Good evening and happy Thursday. What I'm going to actually do first. It looks perfect. So in the chat, there is both a link and QR code to a poll on two options on what to do Monday. So that poll will close Monday at 9 a.m. So Monday, 9 a.m., I will look at the results, and that is what we'll be doing Monday evening. This chat does remain available even after the meeting ends. Right? If you just go back to team, right under the meeting, you should have an option even after the meeting has ended to expand comments, which is what they call it. So the link and QR code will still be there all weekend, so there's no need to do it right away. Okay. So I do apologize for yesterday. Normally I try and grit through it and still hold a meeting, but I think my vertigo kicked in because I was lightheaded all day. And I just was not able to shake it. Still feeling it today. It's a lot better. So we're going to go as long as I can. I'm going to try and get through everything I want to get through. But if it starts to get worse, I will have to stop early. All right, so we're going to jump in. We're going to get through as much as we can. So I should have watched the videos on what an integral really is. Right, and as you saw, it was the limit of a Riemann sum, right? And then we also, or you also looked at the video that described what an antiderivative is, sometimes also called an indefinite integral. Tonight, there are really two things. Our first technique of integration, or first technique of anti-differentiation, called change of variable, and then the fundamental theorem of calculus, which gives us a really nice way of evaluating integrals. So the fundamental theorem of calculus will relate integrals, antiderivatives, and derivatives together, starting with change of variables. This is also sometimes referred to as U substitution. In Calc 2, you will study a different change of variable technique called trigonometric substitution, where you change the variable into a trigonometric function instead of just u substitution. But the principle is the same. You're still changing the variable of integration. All right, what this says so u is some function g of x, where the derivative of g is continuous over an interval, and f of x is continuous over the range of g. Then the antiderivative of f of g times g prime is equal to the antiderivative of f of u du. Right? This is essentially the anti-differentiation analog of chain rule. How did I do this before? Oh, right, I have to do this, right? And so we're going to find the following antiderivatives. And so antiderivative of x times x squared plus 1 quantity 8th power. Right. So when you look at an antiderivative problem, right, which will obviously then lead into an integration problem. First, you want to look at it and see if it fits any of the basic antiderivatives that were given. Well, this doesn't. What we could do here, if we really wanted to, is we could take this quantity and expand it out first, and then distribute that x through. And then we have the antiderivative of polynomial, which we can do. But that is a lot of algebra. In fact, it's an amount of algebra that I'm just not willing to do. I'm too lazy. But what I recognize is that the derivative of x squared plus 1 is 2x. Well, I have an x. So I'm going to say let u be x squared plus 1. Now we need the differential for u. Now remember, differential for u is going to be g prime of x times dx, right? Remember, we did differentials in the last unit. So derivative of x squared plus 1 is 2x. And then we added dx, so there's our differential for u. Then what we're going to get this antiderivative I'm going to rewrite it. Notice that we want a 2x dx so we can get du. Right, we only have the x dx. We're missing that constant 2. But remember, there's 2 things in mathematics that you can always do. You can always add 0, and you can always multiply by 1. If I multiply by 2 and then immediately multiply by 1/2, that's the same as multiplying by 1. So I multiply the x dx by 2, which means I have to multiply the entire antiderivative by 1/2. And there's our substitutions. Antiderivative of u to the eighth du. This is the power rule. And remember what the power rule said. You add 1 to the exponent and divide by that new exponent. Right? Add 1, divide the same. Also, don't forget your constant of integration. I'm going to do 2 steps at once here. I'm going to go ahead and multiply 1/2 by 1/9 to get an 18th. Also going to back substitute. The variable of the problem was x, not u. All right, so we have to do backward substitution. That would be our antiderivative. Again, there are 2 ways to tackle this problem. I think this one I will do both methods. Factoring out that 2 is going to help. Now, the first thing we can do is factor out a 2 from that first term. Now expand it out. All right, now it's just a simple matter of using the scalar multiple rule, the power rule, and the sum difference rule. All right, 18x to the fourth over 4, that can be simplified. It's 9x to the fourth over 2, right? And 63x cubed over 3, that can also be simplified. It's 21x cubed. (43x squared over 2), and then minus 7x, right? And then don't forget your constant of integration. Distribute that 2 through. And then we have our antiderivative. Second method. Again, start by factoring out that 2. But now notice that the derivative of 3x squared plus 7x minus 1 is 6x plus 7. Again, I'm going to rewrite it. You don't have to. It's going to get annoying. So this becomes simply twice the antiderivative of u du. U squared over 2 antiderivative just simply becomes u squared plus an integration constant of integration. Right? Backward substitution. And there you go. Now, just to verify that this result is the same, for Pete's sake. I don't know why I went full screen. If you expand out the quantity squared, right? So here's how I did it. First, I just looked at each term and took the square. And I just started to multiply the terms, right? So I took 3x squared times 7x, doubled it. 3x squared times -1, doubled it. And then 7x times -1 and doubled it. Right, something. Oh, that's because I don't know how to subtract. 49 minus 6 is 43, not 41. Compare that to what we got for method 1. And are they the same? So are they the same results? They would have to be the same, right? Otherwise, we're in trouble. But notice in method 2, when we expand it out, we get a +1 that is not located in the solution from method 1. So how can these possibly be the same? careful how you say that. It doesn't have to be a +1, right? But your idea is, I think I know where you're coming from. 1 plus a constant. Still constant, isn't it? Right? So in a sense, what we can do is we can say, well, we can just write this as some other constant +1, right? Or I can just write this like this. And I'll just make note that C1 was 1 plus C. Right. Remember, it was stated, right, that antiderivatives are unique up to a constant. So yes, these are the same antiderivative, right? They're unique up to that constant of 1 plus C in this case. That is something else that you should keep in mind, is that when you're dealing with arbitrary constants, so when you're dealing with an antiderivative solution, and this is especially true if when you move on to differential equations and you start solving differential equations, you get what's known as a family of solutions, right? Because you have constants involved, arbitrary constants, much like we do here, is the manipulation of constants. Okay, well, look here, okay? Here we seem to have a bit of a problem. No, it's not a bit of a problem. We do have a problem. We do not have a way right now, right? There's no of the basic rules that cover a fraction. Also note there's no way to simplify this. The only thing we can try to do is change a variable. And so let u be x plus 3. That would make du dx. We're now stuck with that x. All right. But remember, we're changing variable. We're changing from x to u. So we can't have that x in the antiderivative. All right. We have to replace that x with some function of u. But didn't we say that u is x plus 3? So wouldn't that mean that x would have to be u minus 3? That still leaves us with the problem of it being a fraction. But this time it can be simplified. U divided by the square root of u. Would be u to the 1/2 power, right? And then 3 over square root of u would be the same as 3 times u to the minus 1/2. Now the rules that we have apply. U to the 3/2 divided by 3/2, which is the same as 2u to the 3/2 over 3. Negative 1/2 plus 1 is 1/2, so we get 3u to the 1/2 over 1/2. And that simplifies to 6u to the 1/2. And then plus some constant of integration. If we write this as a single fraction, And then replace u with, what did we say it was? X plus 3. Okay. Which gives us now our antiderivative. This is what I wanted right here. Perfect. Okay. So I need to take a quick timeout. So go ahead and work on this problem. And then when I get back, we'll go over it. Okay. Sorry about that. Right. Right. We let u be square root of x here. Okay. Which would make our differential for u du, right? 1 over 2 root x dx. Then what we're going to get and again, I'm just rewriting it. Well, look at what our differential for u is. All right. Notice what we're missing is a 1/2 out of the differential for u. So I'm going to multiply by 1/2. I'm multiplying the dx over root x by 1/2. But that means that we have to multiply by 2 as well. right? Because we're only allowed to multiply by 1. This leaves us with 2 times the antiderivative of e to the u du. Now, e is one of the general antiderivatives that we went over, right? It's just 2e to the u, right? So antiderivative of e to the u is e to the u. And that would be our antiderivative. Okay, so what about antiderivative log x over x? Right. Well, the derivative of natural log of x, 1 over x, isn't it? And notice we get the antiderivative of u du. Right? It leaves with u squared over 2 plus our constant. Right? This is one answer. We could also write it this way. So to avoid ambiguity here, what we could do is do that. Right, so it's natural log of the fourth root of x, and that entire function is being squared. And so either of these answers would be acceptable. Now we're going to get into some trig integrals. And these integrals are pretty cool. Because a lot of these integrals can be done with change of variable or trig identities, right? In fact, in calculus 2, one of the chapters is dedicated solely to techniques for evaluating trigonometric integrals, but just about every single one of those techniques can be done in Calc 1, right? You do not need Calc 2 for it because it's mostly trig identities. So this one isn't, right? This one is real simple. This is a U sub, right? The problem with this integral is the sine squared. But notice that the derivative of sine is cosine. Using that substitution, that makes this problem the antiderivative of u squared du. Right, that's just u cubed over 3. Which is sine cubed of x over 3 plus our arbitrary constant. And of course, if we're really ambitious, what we could also do is try and use trig identities to simplify this. Right, so if we didn't want to write it as sine cubed, let's say I wanted to write it as single powers, just an example. And again, this is totally optional, but this runs into the problem that I mentioned before, where if you're checking your answer, right, with, let's say, the back of the book, for instance, they may get something different than what you have, but they're actually the same, right, because they're using identities to simplify. Right, so as I said, just for example, let's say that I wanted to write this as single powers. I'm pretty sure I can do that. I can, yes. Right, we could start by splitting sine cubed up as sine squared times sine. Let's do this. Right, sine squared, 1 minus cosine squared. Distribute that sine through. Right, cosine squared as cosine times cosine. And then use the identity. That 2 sine cosine is sine of 2x. Right, so sine times cosine would be a half sine of 2x. Right, so we could also write it this way. And this is now all single powers. As to what I personally would do, is I would just leave it as sine cubed over 3, because to me that looks simpler. Right, that's 1 term versus 2. It's really just a matter of preference at that point. Right, this was done purely as an example of different ways of representing the same antiderivative. Cosine cubed times sine. Why did my camera get dark all of a sudden? There we go. I just realized I don't have. Hold on. But it matters. Right. Well, notice that derivative of cosine is negative sine. So we just say that u is equal to cosine of x. That makes du negative sine of x dx. We just have to multiply that sine of x dx by minus 1. So we're going to have to multiply the antiderivative by minus. Right, now it's just a simple power rule. And we get c minus cosine to the fourth x all over 4. Or c minus the cosine fourth x over 4. Again, you could write this as a single fraction, but not necessary. Did it again. Okay, what's going on? There we go. Antiderivative of tangent squared x times secant squared x. Well, we have two choices then for you. You could be tangent, right? Or you could be secant. The question then is, which of those choices leaves us with the desired antiderivative? Now, derivative of tangent is secant squared. Derivative of secant is secant tangent. We have a secant squared. So we say u is tangent. That makes our du secant squared dx. That leaves us the antiderivative of u squared du. Antiderivative would be u cubed over 3, right? And so do back substitution, and you're going to get secant cubed x over 3 plus our constant. This one, that's annoying. Whatever. Piss off. Thank you. No. Antiderivative of tangent squared. Well, here we have a bit of a problem. We do not have a general antiderivative for tangent squared. We don't even have a general antiderivative for just tangent, do we? Right. So what are we going to do? Well, if we tried u sub, that wouldn't work, right? Let's try this. See how that works. Or we can recognize that tangent squared is secant squared minus 1. Well, we have a general antiderivative of secant squared. It's tangent. Right, and the antiderivative of 1 is just x. That would make our antiderivative tangent x minus x plus a constant. In this case, we didn't need a change of variables. We just needed trig identities. Now, when we were doing antiderivatives, only two of the actual trig functions, only two antiderivatives are given, right? The one for sine and the one for cosine. With change of variable, we can now find the antiderivative of the remaining four. So let's start with the tangent of x. That is sine over cosine. Let u be cosine. Du would then be negative sine. Notice what we're going to get is negative antiderivative du over u. And if you recall, the antiderivative of du over u is natural log of the absolute value of u. You get either the negative natural log absolute value of cosine of x or natural log of the absolute value of secant of x. It just depends on your source. They are both equally valid. This one, I think I'm going to leave to you as an exercise. To show that for cotangent, the antiderivative, either log absolute value of sine of x or negative natural log absolute value of cosecant of x. Again, just depends on the reference you're looking at. They both occur. You will see them both, so they're both equally valid. So now what about for secant? Remember, you're always allowed to multiply by 1. So what we're going to do is multiply by secant x plus tangent x over secant x plus tangent x. Let u be secant x plus tangent x. That makes du and that makes du secant x tangent x plus secant squared x dx. And notice that's our numerator. This will once again make our antiderivative du over u. And that makes the antiderivative of secant x to be the natural log of the absolute value of secant x plus tangent x, right? Plus the constant of integration. And again, this one I think I'll leave as an exercise. Antiderivative of cosecant of x is the natural log of the absolute value of cosecant x minus cotangent. We now have antiderivatives for all 6 trig functions. So that means that we do not yet have an antiderivative of a logarithm, right? We don't have the antiderivative of log x. Nor do we have the antiderivative of any of the inverse trig functions. Right. Those antiderivatives we cannot yet do. They require the technique known as integration by parts, which is covered in Calc 2. So, sorry to disappoint you. You're going to have to wait till Calc 2 to find out the antiderivative of logarithmic functions and inverse trig functions. Any questions? I will let. Do I want to? No, I don't think I do. I'll do it later if I can. Okay. So then let's go ahead and take our break. We'll go until 8 o'clock, come back, and then we'll look at the whole point of Calc 1, the fundamental theorem of calculus. I will see everyone again at 8 o'clock. Okay, and we're back. So the fundamental theorem of calculus, right? Like I said, this is what Calc 1 has been leading up to. Right? So important, in fact, that not only does it get a name, it gets its own acronym, its own shorthand, FTC. So the fundamental theorem is in two parts. So depending on the source, the reference that you're using, the parts may be different orders. Part 1 for us, I think this is the order that our text uses. If small f of x is continuous over a closed interval a to b, and the function big F of x is equal to the integral from a to x of little f, small f of t dt, then big F prime equals small f of x over that interval. Okay, so what part 1 does is not only does it tell us that we can define functions as integrals, but it relates the derivative and the integral together. Right? What this is saying is the derivative is undoing the integral. Part 2 is usually what everyone thinks of and usually what people refer to when they refer to the fundamental theorem of calculus. Part 2 says, if small f of x is continuous over the closed interval a to b, and big F of x is any antiderivative of small f of x, then the integral from a to b of small f of x dx is big F of b minus big F of a. Okay. Two important terms in part 2. The integrand must be continuous over the interval of integration. That includes the endpoints because it's a closed interval. If it's not continuous, then we have what's known as an improper integral, and that is covered in Calc 2, right? The fundamental theorem does not apply if the integrand has a discontinuity in the interval of integration. Second, any antiderivative typically for part 2, for the fundamental theorem, we use what's called the simple antiderivative. Right, the simple antiderivative is the one where the constant is 0. Right, so for instance, the simple antiderivative of x squared is x cubed over 3. So actually what I want to do A corollary to the fundamental theorem part 2. Has to do with using U substitution on a definite integral. Of course, it just messed up. That's okay. That's a quick fix. And so what it says, right? So, right, we have U being G of X. G prime is continuous over the interval A to B. F of X is continuous over the corresponding range of G. Then the integral from A to B of F of G of X times G prime dx is the integral from G of A to G of B of F of U du, which is big F of G of B minus big F of G of A, where big F of U is any antiderivative of little f of U. Okay. So when evaluating an integral, first thing you want to do is find the simple antiderivative of the integrand. So for this problem, we want the simple antiderivative of 3x squared minus 2x plus 1. Right? And that simple antiderivative, x cubed minus x squared plus x. Then what we do is we evaluate that from 1 to 3. Right. Couple ways you can do it. You could first plug in 3, right? Evaluate it. Then plug in 1, evaluate it, and then subtract. Here's the way I typically do it. Is I just do it term by term. Right? So I'll go first term, x cubed, evaluate that from 3 to 1, or from 1 to 3. That's 3 cubed minus 1 cubed. Then I'll do the second term. That'll be 3 squared minus 1 squared. And then I'll do the third term, 3 minus 1. Right? But again, typically I would, do these calculations in my head, right? So I'd say x cubed from 3 to 1 is 27 minus 1, which is 26. Minus x squared from 3 to 1 would be 9 minus 1, which is 8. And then x from 3 to 1 would be 3 minus 1, which is 2. And that's 20. Right. So just like when we were doing derivatives, right? We had the definition of the derivative. And we saw that while that is great for understanding what the derivative actually is, right? So what we're actually finding. In terms of computation, it was rather tedious, right? So we came up with the derivative function and simple rules, right? The rules for finding derivatives without the limit. And that made it a lot easier to actually compute what the derivative is. Right? Integrals were the same, right? So we looked at what the integral actually is. It's the limit of the Riemann sum, right? And that definition is great for telling us what it is we're actually doing, right? So what it is that an integral actually represents, which is area under a curve, technically signed area under a curve. However, we found out very quickly how tedious that definition is. In fact, it's way more tedious than that of the definition of the derivative, the limit definition of the derivative. Right? So then what do? Well, we discuss what an antiderivative is, right? It's the opposite of a derivative. Which led us to the fundamental theorem of calculus, which now gives us a really quick and simple way of actually computing the integral. Right? This was much easier than using the limit definition. keep in mind that the fundamental theorem of calculus may not always be the simplest method. Right? For instance, you could find an integral that you can easily represent as an actual geometric area, which would make it a lot easier to calculate than doing the antiderivative and then the fundamental theorem. An example of that would be this here. In fact, you can't actually compute this with the fundamental theorem until Calc 2. But if you instead look at this as an area, you would recognize that, well, the integrand is a semicircle. Right? It's the upper semicircle of radius 3. From 0 to 3, we're actually dealing with just half of that, right? So we're dealing with a quarter of a circle of radius 3. Well, circle area is pi r squared, 9 pi. We only want a quarter of that. So this is 9 pi over 4, just using area. I can tell you this would involve, if you were to use the fundamental theorem, you wanted to find the antiderivative, this is trig sub. Right? It's really way more tedious than just looking at it as an area and going, oh, well, this is an area, 9 pi over 4 done. And in fact, I believe it's either the Unit 4 test or the final exam that asks you to calculate an integral by looking at it as a geometric area. Okay, so now we want the integral from pi over 2 to pi of cosine of x. Right, well, again, what we want to do first is we want the simple antiderivative of cosine, which is sine. Right, then we evaluate that pi over 2 to pi. Right, sine of pi minus sine of pi over 2, -1. Okay. Integral from 0 to pi over 4 secant squared x dx. First, we want simple antiderivative. Simple antiderivative for secant squared. Tangent of x. That will be evaluated from 0 to pi over 4. And tangent of pi over 4 is 1, and tangent of 0 is 0. That makes this integral 1. Integral 1 to e, 1 over x dx. All right, so what we need, right, first, simple antiderivative of 1 over x, which is the natural log of absolute value of x. Now, what we can do here is we look and we go, okay, well, the interval's 1 to e, right? X is positive on that interval, so we can actually just drop the absolute values and say this is natural log of x. 1 to e. That'd be natural log of e minus natural log of 1. Natural log of e is 1. Natural log of 1 is 0. Our integral is 1. Integral minus 1 to 1, 5 to the x. Antiderivative of 5 to the x. Five to the x over natural log of 5, right? All right, so evaluate that from -1 to 1. Be 5 minus 5 inverse over log of 5. (24 over 5 log 5). Integral 1 to 3 of e to the x. Antiderivative of e to the x. E to the x, right? If that gets evaluated 1 to 3, we're left with e cubed minus e. Or e times e squared minus 1. So how are we doing so far? Any questions?
No.
Chat. Excellent. Oops. How do we do that? There we go. Integral from 2 to 6 x times the square root of x minus 2. Oh, here we can see that we're going to need to do a change of variable, right? Oh, I don't want, no, I'm sorry. I don't want u to be x minus 2. And it makes du dx. Then the integral from 2 to 6, x times the square root of x minus 2. We're going to get the integral. And so remember, when x is 2, we're going to want what u is, right? Because we're changing from x to u. So we're using this corollary. Okay. When x is 2, u is 2 minus 2. When x is 6, u is 6 minus 2. Right? So u is x minus 2. That means that x has to be u plus 2. When we expand, u to the 3 halves plus 2u to the 1 half. That's what we want the antiderivative of. We want the antiderivative of u to the 3 halves plus 2u to the 1 half. So the simple antiderivative would be 2u to the 5 halves over 5 plus 4u to the 3 halves over 3. Now that gets evaluated. U is 0 to 4. Again, what I typically do is I go term by term. Okay? So I'll go u to the 5 halves from 0 to 4. That is 4 to the 5 halves minus 0. So just 4 to the 5 halves, which is 2 to the 5th, 32. Times 2, 64. We get 64 fifths. Same thing with u to the 3 halves. So that's going to leave you with 8 and then times 4 thirds. Something over 15. What, 192? 160. So that's what? 350 to 352. Over 15. Integral from negative pi over 2 to pi over 2. Sine squared of x times cosine of x. So again, we're going to need to make a change of variable. We let u be sine of x, which would make du cosine of x dx. Now going to be the integral. Sine of negative pi over 2 is -1. The positive 1, u squared du. Be u cubed over 3 from -1 to +1. So 1 cubed minus -1 cubed, that's just 1 plus 1. We get 2/3. Again, this is change of variable. Let u be 1 minus x squared. This means du is negative 2x dx. Right, we're going to have the integral from u of 0, which is 1, to u of 1, which is 0. We're going to need a negative, right, because it's negative 2x dx. And then u to the 4th du. Okay. Keep in mind, nowhere does it say that the lower limit of integration has to be smaller than your upper limit. Right, so this brings in the idea of a direction of integration. Which is touched on more in Calc 3. But the general idea is, right, so instead of going from 0 to 1 this way, right, our path is just the opposite. So think of it like we're walking, we're traversing the other way instead. That's all it is. But there is a property of integration which says you're allowed to flip the order of integration by multiplying by a -1. So if you do not like that order, you can just get rid of the negative and make it 0 to 1 instead. All right, antiderivative, u to the 5th over 5. This will be evaluated now from 0 to 1. And we get 1/5. Integral from -1 to +1. 1 over 1 plus x squared. Antiderivative of 1 over 1 plus x squared, right? And again, we want the simple antiderivative. is the inverse tangent. Inverse tangent of 1 minus inverse tangent of -1. Inverse tangent of 1. Pi over 4. Inverse tangent of -1 is negative pi over 4. You get pi over 2. All right, this one's going to be fun. What we're going to have to do for this problem is look at this and say we're going to want to complete the square, which means I want a +9. Ten is 9 plus 1, so I can just write that as +9 plus 1. All right, so this is going to allow us to do this. Now we need to do a u sub, so let u be x minus 3. du is then just simply dx. We're now going to have the integral u of 2, -1, to u of 4, +1, du over u squared plus 1. But we just did that integral. So it's pi over 2 from above. See that? Okay, any day now would be nice if you wanted to load. Try this. Oh, perfect. Well, technology doesn't want to work with me now. Lovely. Do we have any questions? Since now this just doesn't want to work. Hey. Came back on. That's nice. So we can continue on. Integral -2 to the -1, right? X plus 1 e to the x squared plus 2x plus 1. Clearly, u sub. All right, let u be x squared plus 2x plus 1, which would make du 2x plus 2 dx, or 2 times x plus 1 dx. Negative 2, u of negative 2 is just 1. U of negative 1, which is going to be 0. We're going to need a 1/2 because of this 2 here. And then we get e to the u du. Right? That's a half e to the u. Evaluate that. 1 to 0. E to the 0 is 1. We get 1 minus e over 2 as our integral. Last one for the evening. There's a couple things. Well, actually, one thing we need to do first. We need to factor a 4 out from what's under the square root. All right, square root of 4 is 2. And we're left with 1 minus x squared over 4, which is the same as 1 minus the quantity of x over 2 all squared. Right, and that's under the radical. Now we let u be x over 2. Which means that d would be dx over 2. Our integral then become integral u of 1, 1/2, u of root 3, root 3 over 2. There's our dx over 2, that's just du. And then denominator, we're left with the square root of 1 minus u squared. So the antiderivative of that is just the inverse sine of u. Get the inverse sine of root 3 over 2 minus the inverse sine of a half. Inverse sine of root 3 over 2. Pi over 3. And then the inverse sine of 1/2 is pi over 6. That's just pi over 6. And that would be our integral. Right? That's the fundamental theorem of calculus. Right? Final two assignments are on my math. They will be due on the 12th, which is Saturday. Unit 4 test is also now available. That will be due by the start of Monday's meeting. Right, so tough 5 weeks. We're almost there. Right? We can see the light at the end of the tunnel. You just hope it's not an oncoming train, right? So as I said, I did create a poll. On what we're going to do on Monday, right? So there are really two options on there to go over problems from final exams I've used in previous terms, or to go over the problems that we missed yesterday. Simple majority wins. Tiebreaker is left to me. You should be able to see the results after the poll closes at 9 a.m. on Monday, right? So remember, I posted both the link and the QR code in the chat, right? But they will be available even after this meeting ends. You just have to load up Teams, go to General, you just go to where this meeting was, and you'll see an option to expand out the comments. And then you'll see at the very top the link and the QR code. So don't forget to go ahead and vote on what to do before the poll closes 9 a.m. on Monday. Final exam is next week. Right, the final exam period for this term is 16th and 17th of August. Right now, I have it set where the final exam will post on the 16th and be due at the end of the day on the 17th. So I'll post midnight on the 16th and be due end of the day on the 17th. Okay. Thank you for your attention. And we have one more class meeting left on Monday. So have a wonderful weekend. I will see you all again Monday at 6 p.m.
Thank you.
Thank you.